Okay, good morning, everybody. So we're gonna get started today, and we got a new lesson moving right along. Let's practice the old stuff one more time before we do that. So warm up today. We got three functions actually: f, g, and h. And your job is either do whatever they say, compose them, or divide them, or add them, or whatever the heck it happens to say. So let's see what we can do with this. It says at h composed with g. So that means you're putting the one on the right into the one on the left. So it doesn't matter what their names are. So g goes inside of h. G happens to be this thing right here. So we're going to plug that into h anywhere we see x's. And that will result in square root of not x, because I'm plugging in g, which is negative x plus 5. The x was under the root, so the thing I plugged in is completely under the root. And then we have a plus 2 right there. And we're all done with that. Domain and range. Let's talk about that. That's a weird one. This one is not going to be just negative infinity to infinity. It's going to be a little trickier than that, because there's two things you always got to worry about with the domain: not dividing by 0, but also you cannot have negatives under roots. I got a root right here, an even root, so I better figure out the thing under the root, which is this, right? Can't be negative, so it has to be greater than or equal to 0. Whenever you have a root, you probably want to go set up a little inequality like that and say the stuff under the root has to be 0 or positive. It cannot be negative. And let's see, if you just add the x over, then that means, you can read it backwards, x can only be less than or equal to 5. That's the only places where this is defined. So where are the numbers less than or equal to 5? Well, it's everything from negative infinity up to 5. So this one's domain is negative infinity to 5, and it can actually equal 5. X can be less than or equal to 5, so ended up with a bracket on that one. A little trickier there, a little trickier. But that's really all you're going to have to worry about with domain ever. Like, okay, is there any division? Okay, check for dividing by 0. And if there happens to be an even root, like this, a square root or a fourth root or something like that, you just go off to the side and do that real quick, and then you can figure out what numbers are acceptable. Range, you'd probably have to graph this unless you know something about parent functions. This is kind of like a square root, would you agree? And you should know from sections past that this is kind of a graph of a square root, right? And you should also know that, what's this do inside of here? It kind of flips it over, and the 5 scoots it over. But that's really horizontal things. What's the 2 do? It moves it up 2. So this graph would start here at the number 2 and go all the way up to infinity-ish. So the range is going to be a bracket 2. It can actually equal 2 at height, and then up to infinity. Now it might be over here, I don't know. I got to think about that, but it does start vertically at 2 and go up to infinity. And if that's something, it's too much analysis for you to do, just use your calculator, right? Got your calculators also, so good stuff on that. All right, let's try another one. Number 2. Number 2 is your good friend, fog. For some reason, my 8th hour likes to call it that, fog. But I'd rather say f composed with g. So again, same idea. We're going to plug the one on the right into the one on the left. So we're taking all of g and plugging it into f. So here's g again, but this time we're plugging it into f. So it's not going to be x squared because I'm not plugging in x. I'm plugging in negative x plus 5. So there's the x squared part, but then of course you got a minus 2 also. So there you go. There's f composed with g. And if you were to distribute all this out, I don't know, why not? I would. I'll do it for you. It's x squared minus 10x plus 23. When you square everything and combine like terms, don't kill any puppies. And then that's all the rest of that. Domain, I don't see any roots, do you? I don't see any division. So everything's cool. Everything from negative infinity to infinity. Range is going to be a little harder, though, because that's a quadratic. And you know quadratics always open up. So they have a bottom somewhere. So somewhere from the bottom to the top, we're going to have to figure, go graph it. Let's go find where it is. -2. I agree. So this graph goes all the way from down from -2 up to infinity. So, and again, remember with those quadratics or those even ones or something like that, yes, put a bracket on the interval because it does actually get to that value right there. Never put a bracket on infinity, of course, because you never ever get to infinity. Outstanding. One more to go. Warm-up number 3 today states that you're supposed to be finding g divided by f of x, which means what you think it does, g divided by f. So g is -x plus 5. F is x squared minus 2, so there we go with that. Domain, well, oh, I do see some division, so I got to worry. Can't have the bottom be 0. That's bad stuff. So let's go off to the side real quick and just figure out when the bottom is 0. This is very much something that would be like on your test or something like that from last time. If I just said x squared minus 2 is 0, could you solve that? I hope so. Just move the 2 over, take a square root. Don't forget your plus or minus. So there's 2 numbers, positive square root of 2 and negative square root of 2, that make that bottom equal to 0. So those are no good. So I got to take them out of my domain. Everything except those numbers is fine. So your domain is going to be everything from negative infinity until the first one. First one you use the negative one, negative square root of 2. And then everything between the negative 1 and the positive 1. So everything from negative square root of 2 to positive square root of 2 is okay. And then, of course, we've got to skip over the square root of 2. That's no good. And then, of course, everything from square root of 2 to infinity. So that's why you got to do the work. You know, if you say, oh, it's 1.41 instead of square root of 2 or something like that, I don't give you any credit. You got to do the algebra and get the exact number that causes problems. And range on this one will be very hard to describe. I'll let you skip that one. Any division problems, I won't ever ask you about range because it's just complicated to figure out. That takes a more advanced analysis that we're not quite ready for yet, but we'll get to that in time. All right, let's get the new stuff going. Here we go. LGs today, learn goals. Learn to find inverse relations. Weird topic today. And how do you check if 2 functions are inverses? You might recall from units long time ago, first semester, that an inverse is a function that undoes another function. So we're kind of back to that. The reason this section's in the book right here is because we just got done studying everything with exponents. And the next section of the book will be how to undo exponents, the inverse of that, which are known as roots, square roots, third roots, fourth roots, etc., etc., etc. Thank you. So, of course, notes after you get this copied down. Got another homework over it, of course. 6.1 is due today. 6.2 will be the new one. And the normal business, you'll have a work day tomorrow after we talk about today and all that stuff. So here it is, homework 6.2. Jot it down, page 311. It's online and on, everything's online. But when I say something's online, I mean the online problems through the reveal thing that you like to do, where you just kind of move the boxes around and put things in. That is available. Of course, you're always welcome to do them on paper. Highly encourage that. But it's 5 through 14 all and 18 through 42 multiples of 3. This might be one you actually do want to do on paper just because they do have a lot of weird talky talk in here about restricting domains and all kinds of weird stuff. And I'm going to try, I'd go a little lighter on you, I think, than the grade book would, but you do what you want on this one. All right, 18 through 42 multiples of 3 due Friday. Got 2 days on that. Let's get going. Here we go. This is section 6.2. Inverse relations and functions. A little redundant. Might recall that a relation is anything. I don't care if it looks good or it could be a scribble on the wall. It could be anything at all, but that's what a relation is. And a function, you remember what a function is? Function has to pass the what test? Does anybody remember? Vertical line test. I'm going to be talking about line tests quite a bit today, so get ready for that. All right, here we go with this stuff. Inverse functions. First thing I'd probably write down is, if you don't know it, here's the symbol for an inverse. It's an f with a -1 exponent. It does not mean an exponent. Not at all. And we have done this before, I think, so this should not be anything brand new to you. But when they say f to the -1 of x, they don't mean it's an exponent. The -1 power automatically means it's an inverse. So again, just some light theory before we dive into the stuff as a refresher of what everything does here. A function takes some number x, does something to it, and it spits out an answer, the function when you plugged in x, f of x, correct? And an inverse takes that answer, undoes it, so here's f inverse of whatever I had, so it's kind of like a composition of functions inside of a function. If I take the answer I got out and undo it, I get right back to where I started right there. So functions take numbers and do something to them, and inverses take those things and undo them right there. So you get right back to where you started. In fact, we're going to need that later on in the course. All right, let's see what else we got here today. Oh, you know, when I put some boxes on the screen, they're pretty important. If I took the time to write a box for you, I'm trying to break things down to the simplest level possible. First thing, also theoretically, that when you are finding an inverse, and a graph of something's inverse is the same graph flipped over the line y equals x. And we touched on that a long time ago. So it's back as a refresher. This section in particular will ask you to find things inverses quite a bit. And I'm trying to give you some flat out steps down there, step by step of how to do so. But you need to find an inverse for a function. You call the function something, just for bookkeeping. You don't want to rewrite f of x all the time. F of x, it's just annoying. So you call f of x y. They do that a lot already. They could say y equals x squared plus 2. They could say f of x equals x squared plus 2. It really means the same thing. The key thing is step 2. Switch the x's and the y's. Everywhere you see an x, you don't write x, you write y. And everywhere you saw y, you write x. You literally change their letters. When you change their letters, what you have done is you've flipped the graph or the function over the line y equals x. And then you are now talking about this thing's inverse. If you solve for y, then whatever that is your inverse. And you just call it f inverse then. So steps 1 and 4 are really just renaming something just so it's easier to work with. The real work is number 2, where you switch the x's and the y's, and number 3, definitely when you move things around and solve for y. Not that bad. Well, let's see here. Just as a quick refresher, again, before we dive in with some straight up problems, if I gave you any function, and this is one we're going to study, not the next unit, but the one after that. We're going to study things like this that grow fast, faster. It's called exponential. You don't need to know that. But really, anything, no matter what I give you, if you flip it over this line, y equals x, then whatever you get out is the inverse of this thing. So that's always how you find an inverse. Let's say I gave you this thing right here. Well, it's a weird looking thing, but if I want to find its inverse, if this is the function, its inverse would be this flipped over. And that's kind of what it looked like right there. So you flip it over the line and y equals x. When you flip something over the line y equals x to find your inverse, what you do for any point on this line is you interchange the x's and the y's. The y's become x's and the x's become, and that's what inverses do, don't they? They take inputs that become, or outputs, and they switch them, right? The outputs become inputs, and then you get back out what you had originally. So if x is turned to y's, then the opposite would be y's turned back into x's, and you kind of switch your x's and y roles in that case. So graphically, that's what I really want you to understand. You're flipping over the line, y equals x. I cannot overemphasize that part right there. Now, we're not going to probably go to graphs quite often. We're going to do more things like this. So let's write down this example. Find this inverse. We're going to follow those steps that you just wrote down. Takes all the thought out of it for you. So the only thing we can possibly mess up is like the normal stuff, you know, negatives and something like that. So here's this function. This function takes an input, x, multiplies it by 3, adds 2 to it, and spits out an answer. That's what this function does. So we're going to try to undo that. Now, you probably already see what's going to be buried in the answer already. If this has a times 3 in it, somewhere in the answer, guess what there's going to be? A divide by 3, because they're opposites, correct? And there's a plus 2. Guess what's going to be in the answer? A minus 2. Yeah, somewhere, somehow. So you can kind of expect the opposite operations to be in your answer down here. But your steps are, the first thing is, step 1, call f of x, y, just so you are working with x's and y's. You haven't done anything at all. That wasn't a very productive step. This way you can just work with x's and y's. Step 2 is to switch the x's and the y's. And by that, I mean literally their names. Oh, this is y. Now it's x. There's a 3. Oh, there's an x. Now I'm going to call that y. And as soon as you've done that, what was going in x is now what's coming out. You're switching inputs and outputs in this regard. Then the third step is you solve for y. Not very hard. We're just going to move the 2 over. And divide by 3. So this is what y is now. But remember, as soon as you've made this step, and that's why I put this little dashed line here. Above this, I haven't switched the x's and the y's. We're still talking about the original function. As soon as you switch those x's and y's, now all this work is about the inverse function. So you call this thing you got out the inverse. So your answer on this one is f inverse is x minus 2 over 3. And you can see the opposite operations inside there. There's a minus 2 as predicted. There's a divide by 3 instead of a times 3. Now we're pretty much done with that. They might ask you for domain and stuff like that too. Now this is just a line. It's an x to the first thing, right? So lines go all the way up and down forever, would you agree? So this thing's domain. Well, I don't see any division. I do see some division, but can I divide by 0? No. So the domain's everything. And like I just said, the range is also everything because lines go all the way up and down. That's pretty much it. Let's try another one. Let's do this check. F of x is negative a half. Might have to undo a fraction or something. That's okay. Just keep doing the same procedure no matter what it is. Step 1, call f of x y. Didn't do anything useful, just rather write y than f of x over and over again. And then as soon as you switch their letters around, you're talking about the inverse now. So x instead of y. Negative 1/2 y plus 1. And now we're in inverse world. Every bit of work I do from now on is about the inverse. And just like any function, I want y equals. So I'm going to go solve for y. If you move the 1 over, you got this. And I know you guys hate fractions, so I wouldn't want to divide by a fraction. What's over here that I could get rid of? Well, I could divide by negative 1/2. I could, right? But then I have something divide by negative 1/2. That's kind of weird. How do you get rid of the divide by 2? Well, you could multiply by 2, correct? But then I'd still have a negative, wouldn't I? Well, let's multiply through by a negative. So on both sides, we're going to multiply by negative 2. So on this side, and note I wrote the negative 2 times the whole side. We get negative 2 times x minus 1. And on the right, when you multiply by negative 2, well, 1/2 times 2 is 1, and a negative times a negative is positive. So I got positive 1y, or just y. Which was the point? Which was the point? And that's fine. It's a little weird that it's factored. So if I distribute it out, I get negative 2x plus 2. And while I'm at it, what's the last step? Don't call it y anymore. call it f inverse of x. And this example would have the exact same domain and range as the last one. There's no even roots. There's no dividing by anything with x's, so I don't have to worry about taking anything out like that. And the range, it's a line again, so it will go all the way up and down from negative infinity to infinity on the range. Pretty much it. All right, now this one probably needs some theory behind it before we do this, and the book did a bad job of this. So please, let's talk about this little example. I do want you to write this down, because this kind of gets to the heart of what we're doing today. Not every function has a nice, pretty inverse right off the bat. Here's one we've been studying quite a bit this year, x squared. That's a simple function. It's quadratic. It opens up, blah, blah, blah. If you take this thing, now before we do, is this a function? Does it pass the vertical line test? Yes, it does. So, okay, just heads up on that. But if I take this thing and talk about its inverse, and whenever I talk about an inverse, I'm thinking graphically, I'm going to flip it over this line, y equals x. If I flip it over there, it'll look more like this right here. And I got a problem with that red graph. A red graph annoys me, because this red graph is not a function. If you do, does it pass the vertical line test? No, it does not. So something is not okay, because we always want functions in this class. If I say, go find this thing at 5, I could get 2 different answers out. I don't want that. One of you could give me this value. Another one of you could give me this value, and you'd both be technically correct. We want functions to give out one thing. Well, how are we going to do that? Here's the trick. And it's called a restricted domain. And this is your vocab term for the day. Restricted domain. This is when you literally erase part of a function so it passes the horizontal line test. I'll come back to that in a second. I was just harping on vertical. Why are you talking about horizontal? Which means its inverse will pass the vertical line test. And that means it'll be a function. This is a very weird topic. I'm not going to hit you hard on this one on the test. Honestly, I think you'll struggle with this a little bit. Well, what are they talking about? Let's go back to this graph real quick. For this black one, the original function, I think you could all agree that its domain has every number. It's defined everywhere. But that's a problem, because if I use this whole black line as this function, and then I find its inverse, I get this red thing out that is not a function. It does not pass the vertical line test. That's the big problem here today. So here's what you literally do. You erase part of this. And by the way, if this one fails the horizontal line test, see this is horizontal? Guess what? This one fails the vertical line test. Because when you flip it, horizontal lines become vertical lines like that. So here's the deal. I need this thing to pass a horizontal line test so that this thing will pass a vertical line test. And what you do is you cut off part of this. So here's an example. You could cut off the left side. Might want to jot down that picture right there too. If you cut off the left side, it's just gone. And then you took this black line and flipped it over the axis, then there wouldn't be this top half anymore. If I take this thing and, well, what would it look like? Probably, actually, it would be the top one. If you take that original black one and flip it over the line of y equals x, then you have a piece now, this thing right here, f inverse of x, that does pass the vertical line test. And that's what we want. So how do you just erase part of something? The point is, you don't say it exists over here. You're saying it only exists from this part on. So we're not going to say its domain is all numbers. We are now going to say this thing I'm studying, so it has an inverse. This thing's domain is only going to be, in this case, from 0 to infinity. Because what part did we erase? We erased the part over here that was from negative infinity to 0, correct? If I do that, then when you flip it over the line y equals x, the thing you get out is a function, and that's what you always want. So that's a lot of weird, heavy stuff. That's probably too theoretical for here, but let's try to summarize this thing. If your function fails the horizontal line test, so if that happens, erase part of it so it does pass the horizontal line test. That's essentially the big idea behind restricting a domain. I give you any weird looking function in the world, and you need to check does it pass the horizontal line test, and if it doesn't, you need to erase part of it so that it does pass the horizontal line test, which is kind of strange. This is always a weird topic for kids. And let's try one. Here we go. So write down x squared plus 2x plus 4. You probably do want to graph this thing because it's a very visual argument right here. So take a second and graph it before we do. Very random topic today. Get a graph that kind of looks like mine? Something like that? Okay, looks good. So I look at this thing and I say, okay, I want to go find the inverse of this thing. But the problem is you got to restrict the domain because this thing fails the only test you got to worry about today is the horizontal line test. If this fails the horizontal, then this inverse will fail the vertical and life is no bueno. So you need to erase part of this. Now, I recommend every single time you just erase the left-hand side, okay? So this part is gone now. You're going to restrict this domain. It does not exist over here anymore. You don't want it to exist there anymore, or else this whole world falls apart. So where does it exist now? And look what you have still. Does this pass the horizontal line test now? Yeah, okay, you're on the right track if this thing passes the horizontal line test. Well, that means I can only define this thing not from negative infinity to infinity, but from here on. Would you agree? And if you do second calc and figure out what the bottom is, it's at -1. So this thing's domain, I'm going to force to be just -1 to infinity. Just going to make it that half so that it passes the thing. That's really all you got to worry about with this restricting the domain. Okay, if they say you got to restrict the domain, look at the graph, erase the left-hand side if you need to, and then just say where it exists from here to there. After you do that, finding the inverse is actually the exact same thing we just talked about. Okay, what's the process to find an inverse? You call f of x y, right? We're doing the same thing we just did. Ew. They really want us to do this? Golly gee, they do. Okay. Y equals x squared plus 2x plus 4. That's fun. So, how do you find an inverse? You switch your x's and your y's, correct? So this is x. And now every x is y. Oh boy, you're going to hate me for saying this. All right, now how are you going to solve for y? Probably have no clue. I don't blame you. That's fair on this one. Here's what you would have to do to solve for y. You're going to have to do that skill that you hated a long time ago. Remember completing the square? Do you remember that? That sucks. Let's refresh on it real quick. Write down this equation again if you forgot what it is. Oh, no. I'm so sorry. I promise I would not do anything like this to you on a test. I promise. Promise. The book will. Book's a jerk. It's not me. It's the book. All right. So here's what you're going to have to do to solve for y. You're going to have to complete the square. On this side, you might recall from completing the square that you have something squared, and we're using y's instead of x's, but it's the same concept. If you have something squared plus a number times something, you can write it in this format. This is called completing the square. And you take the number here, you divide it by 2, and you just plug in this equation like it is. So these two right here, I'm going to complete the square on. In this equation, we're not using x's, we're using y's, and b would stand for 2. So according to this equation, it's going to turn into this side right here, which is not x's, but y's. So y plus, I'm copying this down right here, b over 2. Now b was 2. And 2 over 2 is 1, right? So it's going to be just y plus 1 squared. And also, according to my formula, you have to take away whatever b over 2 squared is. B is 2, 2 over 2 is 1, and 1 squared is 1. So here's the completing the square part. Of course, you can still got the plus 4 chilling out there. It really didn't do anything. Now, that was a weird way to solve this thing. That's going to be 3. The reason you'd want to complete the square on this is the same reason you always wanted to complete the square. You can solve for the y thing now by getting this by itself and taking a square root. So if you move the 3 over, that means x minus 3 is y plus 1 squared. I got something squared. It's time to undo it with a square root. So on this side, not much I can do with that. It's just square root of x minus 3, correct? And then the other, okay, and also don't forget your what? Plus or minus, I just took a square root, correct? Yep. And then that equals, well, on this side, I took the square root of a square, so they cancel out, we're done. And the last thing, all you got to do is move the y, or the 1 over. And you're going to get y is negative 1 plus or minus the square root of x minus 3. Now here's the rub. Notice that this answer has a plus or minus in it, right? That's 2 answers, correct? Why is there 2 answers for this? I thought it should just get out a function, not 2. Well, this comes from the fact that if this piece was here, and it's not, right? We took it out. If the piece was here, well, if I took this part and flipped it over the line y equals x, it would look like this. And if I took the dashed line and flipped it over the line, it would look like this right here. Essentially, when we erase this part of it, the inverse, we erased that part. One of these answers is the top one, what we want, and the other one is the bottom one that we don't. Can you guess which one, the plus or the minus? Guess which one goes up? The plus one does, right? And the negative one doesn't. So when you do the work, you get out 2 answers because there is a top and a bottom piece. But since you erase this, you've erased that too, which means you should only use the plus version in this case. Very hard section today. I'm sorry. I feel kind of guilty. A little bit. All right, let's try another one. Ooh. I know we gotta do one more like that. That was just not good enough. All right, one last one. Here we go. If you can do these, you can do anything. I'll give you a very similar one. I'll make it easier on you though, okay? How about this? Here's your function. X squared plus 6x plus 9. This will not be nearly as bad mathematically. All right. Well, let's see what we can do here. First off, what does this thing look like? If you go graph this thing, let me think about it. I don't know. If you went and graphed this thing, it would look like that. It'd be a quadratic opening up. It would bounce off the origin, or off the axis, excuse me. You'll see why in a minute with multiplicities and all that crap. But this is the same problem. Its inverse is not a function because this thing fails the horizontal line test, okay? So again, just erase part of it. I always recommend you just erase the left side of it. If you erase this and then do your test, it passes it just fine, right? So right off the bat, this thing's domain is not going to be all the numbers. I have to restrict the domain and make it smaller so that this thing works out. It'd be everything from this number on. This number turns out to be -3. So it can actually exist at -3 to infinity. So they might ask you what the restricted domain is or something like that, and really just visually draw it and erase part of it and tell me where it doesn't get erased. Let's find the inverse now. Here we go. Same procedure as last time. We're going to call this thing y. And once I call y, then we're going to switch our x's and our y's. As soon as you switch your x's and your y's, you are in inverse world. So everything now is about inverses. Now, could complete the square again. In fact, you probably would want to do that no matter what, just because you don't know. But I gave you a softball because this does factors. Anybody see how this factors here? 3 and 3, right? It factors into something times itself or something squared. So if it turns into something squared right away, you don't have to complete the square. You can just write as something squared. If you can't write as the exact same thing times itself, then you got to go back to that stupid thing, and it really sucks. But we're almost there now. If the thing is squared as x, then you just take a square root, right? Don't forget your plus or minus. So I took a square root of both sides. The squared side just cancels. The other side's always got the plus or minus. And then just move the 3 over. So y is -3 plus or minus the square root of x. And don't call it y because this represents an inverse of the original, what I started with. So we'll call it f inverse of x. Which one do you pick, the plus or the minus? Do you have a guess from experience? Probably plus. Yeah. If I flipped this thing over, again, kind of visually what's going on. Here's the line y equals x. If I took the piece I kept and flipped it over, it would look like this, right? If I took the piece I threw away and flipped it over, it'd look more like that. So this is the plus one because it's going up, and this is the minus one that's going down. So yes, you want to keep this and keep that. So you get rid of the minus, so you make it a plus. Tough stuff today, tough stuff. I know when it's hard. This is hard. All right, let's cleanse our palate with the very last topic then today. So please write this box down right here. This is to verify if two things are inverses. All this stuff up to this point is can you just find an inverse of something? This next topic is if they give you two functions, can you find out if they're inverses of each other? Do they undo each other? If somebody gives you a squared function and somebody else gives you a square root function, they are opposites of each other. There should be a way to check if they are. And it goes right back to what we talked about in the beginning of the lesson. Right, so again, let's just talk about inverses as a theory. As a theory, inverses, well, functions take numbers and spit out something correct. An inverse should undo it. So if I have two functions, let's call them f and g, okay? They're going to give you two random functions, f and g, and your job is to check whether they're inverses or not. Well, that means if I plug x into one of them, and then I take that answer and I plug it back into the other one, I should get right back to where I started with x. Would you agree? And that's what that crap is saying. What's another way of saying plugging a function into another function? Because here's a function. I'm going to take that function and plug it into another function. Well, we just studied that. That's called a composition, correct? So if you take these two functions and compose them together, you should get right back at what you started, which is x. And it goes the other way too. I could flip the diagram around. Instead of starting here and going there and then here, I could start here, go there, and come back, and I should get to the same spot again. So g composed with f should also equal x. This is your algebraic test to see if two things are inverses. If you compose them together, and no matter which way you do it, f composed with g or g composed with f, if you take these two things and put them inside each other, if you always get out x, then these things are inverses. And if you don't get out x, they're not. So it's actually not that bad. Let's try one of these right here. Determine whether these two functions, they give you two functions, h of x and k of x, using interesting letters right now. To see if they're inverses, we're going to compose them together, put one inside the other, and see if it equals x. That's all you got to look for. So write it down, h of x. It looks promising. They kind of look like inverses, would you agree? One's got a square, the other one's got a square root. Those are opposites, right? One's got a plus 13, the other one's got a minus 13. Those are opposites of each other. So it's promising. Let's see if it is. All right, so it doesn't matter which one you do first. I'll do h composed with k first. Let's see what h composed with k is. We're going to compose them. We're going to see if we get out x. And like you just learned in the last section, what's that mean? You're taking k and you're plugging it into h, right? So here's k. I'm going to take that. I'm going to plug it right into here. And we're going to see what happens. Square root of, well, I'm not plugging in x. I'm plugging in k, which is x minus 13 squared. And you got a plus 13 there. Do you see anything canceling out or anything like that? Did this root cancel with this square? The answer is, well, actually, normally it would if this wasn't here. If you had something squared in a root, they would exactly cancel out. The 13 kind of jacks it up. These don't cancel out anymore because you got this plus 13 right here. So is this turning into x then? I don't think it's really going to turn into x. What would this have to be to turn into x? It would have to be x squared. Would you agree? If this was x squared, then the square root would be x. I don't think this is x squared, do you? If you distribute this out, this times this, and add 13 would be x squared. Not exactly. It'd be some other crap. In fact, if you distribute out, you did x minus 13 times another x minus 13, and took time to distribute out, you get this old big old mess. I don't think that's exactly x squared, do you? So when I take the square root of whatever this is, it ain't going to be x. So these are not inverses. You can stop your work as soon as you're kind of sure that that thing is not going to turn to x. I don't think that thing is going to turn to x. So those are not inverses. You don't even need to check the other one then. You should, if this was x, you'd check the other one too. You'd say, okay, what's k composed with h? And you go see if it equals x, and we go that. Let's try another one of those. That was too rough. One last one on the fly. I'll make up one that will work out for you. So we'll keep it real simple too. Nice, simple, clean, linear equations for the last one. We'll call it a day. Here we go. Let's say f of x is x plus 5 divided by 7. I'm going to give you a random another function. 7x minus 5. And somebody asks you to show if they're inverses or not. Well, let's find out. Whatever the two functions' names are, I don't care, f, g, h, w, p, who cares? You compose them together and you see what you get. So in this case, this means I'm plugging g into f, right? So I'm going to take all of g and plug it in for x in the f equation. So that's going to be not x anymore, but 7x minus 5. Of course, still on top, you have a plus 5 and a divide by 7. Now, I think you can see it turns into x right now. Because on the top, the negative 5 and the 5 are 0, right? And 7x divided by 7 is, in fact, x. So this is looking promising. It's like, oh, I put one side, the other, got x, are probably inverses. But you do need to take the time to try the other one, too. Don't just go one way, f composed with g, try the other way, g composed with f. It's like a 99.9% chance if you got x for one, you'll get x for the other, but check anyway. And this means plugging f into g. So I'm going to take this whole f equation and plug it in for this x and g. So now I'm going to have 7 times what I'm plugging in, which is x plus 5 over 7. And what else is inside of g? Well, we have a minus 5, right? So 7 times the thing minus 5. And you see, look what cancels. Do you have a 7 and a divide by 7? Well, those go away. And then what's left? X plus 5. What's x plus 5 minus 5? It's x. And therefore, these two things are inverses. So this is a very awkward section, and I apologize for that. But it's good for you. It's very good for you. I will be very forgiving on the restricting domain things, okay? So you might want to do it on paper, so I'll go soft on you. But of course, you're welcome to do it online, 6-2. You'll have all tomorrow to work. Have a good day, everybody.